why we're interested in all this. And alpha stable motion, and then this idea of walks in and out of balls, which I won't have much time to describe, but I'll give you the setup for it. Okay, so let's get started on our random walk. So can you see the top of the screen? On my screen, it's overwritten with a menu.
Sure.
You can see it. Oh, there you go. I can move that out of the way. Move that completely out of the way. All right. So random walk on RD. So we're going to let Z1, Z2, Z3 be a sequence of independent, identically distributed random vectors in RD. So D will be the dimension of the space we're looking at. And we're going to define these random sums. So X0 will just be some starting point, little x. X1 will be Z1. And then we just add each one of these independent increments on there. So we think of taking a walk, a step. I'll show you a picture in a second. But at each stage, X3 is X2 plus Z3, etc. In general, we do this. And if we think the subscript is time, then we can think about walking around, making jumps around in space. And these connected values give us a random path. Okay, so here's an example. Start, in this case, at the origin. Take one step over here. Then we take another step, and we take another step, another, and another. You'll see we may cross itself and move around and things like that. So that's a simple random walk. A generalization of this is what's called Brownian motion. And it wasn't until yesterday, or the day before yesterday, I guess, that I really looked a little bit at the history here. So it's named after Robert Brown, a botanist, British botanist in the 1820s. But it turns out there was even earlier than that, there was I think he's a Dutch physicist who was looking at coal dust sitting on the surface of alcohol, and he watched these little particles of coal dust bouncing around. Robert Brown was doing the same thing as a botanist, looking at pollen grains in water under a microscope. He saw the pollen grains bouncing around. Louis, oops, not Louise, it should be Louis Bachelier, also worked with Brownian motion to model stock prices and some finance type problems. This guy named Albert Einstein, in 1905, one of his multiple papers in that incredible year, you basically came up with the idea of Brownian motion to help describe the atomic theory of fluids. It's kind of funny to think about it now, but at that time, 115 years ago, people weren't sure if the atomic theory of matter was really right. Apparently, physicists had come up with this as a possible explanation, but nobody had really tied it to physical things that you could measure and observe. So after Einstein's paper, John Perrin, I think it was around 1970, he used the ideas in Einstein's paper to actually calculate Avogadro's number and tie physical meaning to what atoms are and how many of them there are in space and stuff. He won a Nobel Prize for that work a few years later. And then finally, for mathematicians, Norbert Wiener gave a rigorous definition of Brownian motion on a path space. So I'm not going to be rigorous about it here. I'm just going to say that Brownian motion is a continuous time random process. So we're generalizing the random walk we saw there. So it's not just at discrete steps, but it's at all positive times t. We start at some location. We have stationary independent increments. So this is the difference, the change between time s and time t. And that's going to be multivariate normal with mean 0, and then have be radially symmetric with variance proportional to the difference in time. So on small intervals of time, we have small steps. On bigger interval of time, we have bigger steps. And so intuitively, what we're doing here is we're going to zoom out on the previous plot, which we saw here, scale appropriately, and then go to infinity. And here's a short simulation in 2 dimensions. Again, we start at the origin, and this path jiggles around. So the scaling keeps things finite, but there's a lot of irregularity in these paths. If this is a simulation with 5,000 steps in the path. And I'll point out that these are random paths. This is one possible realization, or more precisely, this is a discrete approximation to one possible realization. There's an uncountably infinite number of paths, and they jiggle around that. Okay, so to give some definitions, I got to do some basic, some background here. So if we have a continuous time random process, we'll say it's transient if the limit as time goes to infinity, the absolute value is infinite. So here's a sketch here. The walk starts, makes some steps around, but eventually it starts drifting off and eventually goes to infinity. Okay? So that's transient. Recurrent is the other possibility, and the kind of processes we're looking at, there's a dichotomy. Either you're transient, that is you run off to infinity, or it must be recurrent. So in this setup, we're starting at 0, so we can move around, but we always come back to 0. Maybe not exactly 0, but arbitrarily close to 0. So a mathematical statement of that is this: the limit of the absolute value is 0. So at arbitrary large times, we get arbitrarily close to 0. So you keep coming back, hence the term recurrent. So it turns out Brownian motion is recurrent if dimensions less than 3 and transient if dimensions 3 or higher. So the idea is in 3-dimensional space or higher space, there's a lot of room, and this bouncing around random path will tend to wander off to infinity. In dimension 2, there's not that much room. There's not dimensions, there are not directions we can go. We keep coming back to any location. Okay, some noise there. Hitting time and locations. So we're going to take a compact set K. These gray balls are an object, and I want to talk about hitting that. So I start the process. In this case, again, this is a discrete realization of what I'm talking about. I start the process, and it bounces around, taking steps until it hits the object. So if it's transient, it may never hit the object. If it's recurrent, it will always hit the object. Okay? So we're going to let T, capital T, be the smallest time, positive time, where the process is in the set K. And this depends on the random path. So even if I start at the same location, same point, I'll get a random path. The jumps will be random, and so I'll have a different path, and I may or may not hit the set, and then I'll generally hit it in a different point. Okay, so x of t is a random time, and now I'm going to do something more general. I'm going to take the continuous time random process x and evaluate it at the random time, capital T, and this gives you the process that stopped at t, so it's the first hitting location of k. So in this illustration here, it took 35 steps to hit this target set K, and it hit the hitting location is right here. So this symbol is a bit complicated mathematically, but what it does is it gives you a distribution on this set. Okay? The ones that are more likely to be hit, there's more probability there. Points that are less likely to hit. And so this in general always depends on where you start. If I start over here, it's much more likely I'll hit over here on this side and back here somewhere. Okay, so just some brief properties of Brownian motion. So with probability 1, the paths are continuous. So that says these hitting places, these hitting locations will always be on the surface of the region. However, even though it's continuous, the paths are nowhere differential. So there's no place where you have a derivative. These paths are so irregular that you have a Hausdorff dimension. So it's very simple. In this Brownian case, the Hausdorff dimension of the path is the minimum of 2 in D. So in even though it's an image of a line, it's so irregular that it fills up space. It gives you generally a two-dimensional object. Actually, there's a typo there, so I'm going to skip that one. Let me see if I can do this demo. So here's a demo of where Brownian motion comes up in the atomic theory of fluids. So these little gray dots, which are bouncing all over the place, are meant to represent water molecules, or the molecules of whatever fluid you're in. And it's hard to see it, but there's a little, these blue paths are a bigger particle. In Brown's case, they're pollen grains, and they're being bombarded many times in any small interval of time by all these water molecules, and they have a motion. So these blue curves are multiple paths going on.
John, quick question.
Yeah.
In the last result it is Hausdorff-Besicovitch dimension 2 almost surely?
Yeah.
Wow, okay.
With probability 1. So there's a significant amount of measure theory behind all this stuff. What you really have to do to construct Brownian motion properly, this is more about Wiener's idea, is define a measure on a function space. And then you show that the support of that measure is actually within the subset of continuous functions. And there's a lot of 0-1 laws going around. Something either happens all the time or it happens none of the time.
Right.
Okay, now I'm going to change directions a little bit, but we'll see that they do tie together. Shapes. So here's a very simple shape, a unit ball, something that we're all familiar with that we can deal with. Here's something a little bit more complicated, but still pretty simple. Here's an object that is more complicated. It's a union of balls. And then here's something that's even more complicated. So you can think of this as a cross-section of a sort of pipe that has a irregular interior. Okay. And we want to understand something about the shapes of, well, characterize something about the shapes of multiple objects. In particular, this is Jack Douglas's, one of his main focuses. If you have something like a chain polymer, so here's a polypropylene model of a molecule. You have all these different atoms sticking together. And then the next one is a picture of a star polymer, where you sort of have these arms coming out from the central region. These are complicated modules with very complicated structures. And in general, when you make them, these are constructed with a process that they'll come out in different shapes and different sizes and different structures. And we care about this because the shape determines many physical properties. There's a famous book by Polian and Jago about isoparametric inequalities in mathematical physics, which is related to this. So electrical properties, so if I have a complicated object, its shape determines how it interacts with other objects. If all these particles are together and they're trying to flow it through some sort of tube passageway, how well they flow. If it's a simple thing like a ball, they bounce around and go through rather quickly. If it's a complicated thing like that star polymer, they'll run into each other in the wall a lot and it'll be very sluggish to move. And other things like radar cross-section are all important things that we care about. So we want to study these complicated shapes. We're going to use random walks and mean times. So here's some more mathematical, couple pages that are more mathematical. So this is potential theory. And I'm going to start with the work of Marcel Rees in the late 30s. He generalized capacity. So I'm going to pick an alpha, a positive number alpha. I'm going to define the alpha energy integral for if I have a probability measure on a compact set K. Again, this would be an RD. So we take the double integral over the cross product of K with itself. And then we integrate this kernel, 1 over x minus y to the d minus alpha, times the product measure for the measure nu. And then there's a constant up above. So what that constant is, different people choose different constants. This is the main idea. Okay. The alpha capacity is the lim of the alpha energy intervals over all probability measures on K. So there's a lot of theory here, but there's the one thing that we're going to take for granted is there's a unique measure that minimizes this, and it's called the equilibrium measure. Okay. And so when D is equal to 3, so in normal three-dimensional space, the 2 capacity of an object K is the classical capacity. And here's a quote from Polya. To find the electrostatic capacity is a clear-cut, relatively simple problem in applied mathematics. Yet many familiar solids, we don't have a fluid, and they have little hope of ever obtaining the exact expression for it. Okay? So we want to try to understand capacity for more complicated shapes, especially something like a polymer, which may have thousands of atoms in a very complicated structure. And only yesterday, I found this footnote in this paper by Polya. It's sort of a mini Fermat's last theorem. That claimed, Jacobi and Kirchhoff claimed that when just before Dirichlet died, that he had solved the problem for a particular shape, and that solution appears to be lost. So, who knew that there may be a mini Fermat's last theorem type thing going on here? Okay, so now I'm going to tie together this idea of hitting distributions and capacity. So let's let mu be the distribution of the hitting locations. So again, in this Brownian motion case, we've got a measure on the surface of whatever our object K is. Okay? It turns out that that distribution is exactly the equilibrium distribution of charge on the boundary of the set K. So that means that and therefore the 2 energy interval is minimized by that. Therefore, the alpha capacity, this should say 2, it should be cap 2. So the 2 capacity of K is 1 over the energy interval evaluated at that measure. Another connection here, so we're tying this to a lot of important ideas in analysis. So given a function f0 on the boundary of the set, if I take a point outside of K, I can start a process at that point X, and then I run it till it hits the set K. Okay, and that's a random location. So I can take the expectation that of all possible locations. There's a function missing in here, sorry. There should be an f0 around X of t here. Darn it. Mistake on page 2. So if you take the expectation of f of x of capital T, given that you start at xt, that defines a function, depending on where you start the process. That turns out to be a harmonic function on the complement of K, and it agrees with this f0, this boundary function on the boundary. So we have solved Laplace's equation. Okay? F is the function that has Laplace equal to 0 on the complement of K and agrees with the function f0 on the boundary. So there's an intimate mathematical connection between these random hitting locations, these ideas capacity, and certain elliptical PDEs, which is why people like Polya and Jago and other people were studying these things. Okay, so going back to Polya's quote that there's very few objects where we can actually find the capacity exactly. Jack and his group out at NIST developed this program based on random walks that allows you to compute the capacity to high accuracy. And it's based on random walks. So there's this paper by several people, including Jack and Deborah, who implement this hitting algorithm for Brownian motion when alpha equals 2 and dimension D is equal to 3. The idea here is you start many Brownian paths, and you see where they hit your target. So you can have a complicated object, and you can start many random walks and see where they hit, and you can use that information to get an empirical distribution that approximates the law of the hitting locations, and then you can estimate the 2 capacity from that. There's actually a simpler way of doing it in the case 2, alpha equals 2. And then a few years later, they came up with a significant speed up using this idea of walking on spheres. It goes back to Mueller in 1956. I don't want to get too distracted in that. Okay, what I want to talk about is what we're trying to do now, what we are doing right now, is we want to generalize this classical Brownian case to what's called an alpha stable case to allow accurate calculation of this alpha capacity. So Zeno will calculate the 2 capacity, a very complicated set, so we want to be able to do the same for alpha capacity using this connection with random walks. Okay, so alpha stable distributions, Paul A.V. Generalized Brownian motion. So the idea is instead of the increments, these steps being Gaussian, we're going to use a different distribution. So we're going to use stationary independent increments that have an alpha stable distribution. And I won't try to explain all this stuff, but the joint characteristic function looks like this. So remember x of t is a vector value. So this is the dot product here. I take a vector u dot product with the increment here, and then take the expected value of the exponential with the I inside it. We get the joint characteristic function of the increment, and it looks like this. Okay. If alpha equals 2, we get a squared up in here, and this is just the characteristic function of a normal distribution, multivariate normal distribution. Okay. So it turns out we can simulate the increments for these stable steps, and therefore a discrete approximation of the alpha stable motion. And as you vary alpha in this range of 0 to 2, you get increments that are more and more likely to have large jumps. So since we're talking about stable distributions, and since Christmas is coming up soon, or Hanukkah, and you're looking for gifts for people you really know and love, there's this new book that just came out. It is physically available here. It'll explain a lot of stuff about stable distributions. It doesn't have this information yet, but it has a lot about stable distributions. Couldn't resist a little plug there. Okay, so here's a simulation of alpha stable motion when alpha is 1.75. So again, it jiggles around a lot. What you can't see very clearly is, well, you can start to see, there's places where you make a jump, a noticeable jump. Okay? And in fact, no matter how small you look at things, whatever small time interval, there's going to be jumps. And notice the scale here. So this goes from -200 to 200, -200. As I lower alpha, here alpha is 1.5, the scale is getting bigger and bigger. So I'm looking at a bigger and bigger window. And again, you start to see more and more jumps here. And here, if alpha is 1, now notice the scale here. It's going up to 6,000, 7,000. So it's more than 10 times what we started with. And one more here. Oops, no, I guess I don't need that one. So as alpha decreases, you get more and more erratic behavior. There's a lot of local fluctuations going on, but periodically you'll take a big jump out in some random direction. And the tails of those jumps, the tails of the distribution of the sizes of the jumps are governed by one of these stable distributions. So with probability 1, the alpha stable motion is recurrent if the space, the dimension of the space is less than this parameter alpha. It's transient if the dimension of the space is bigger than this parameter alpha. And the paths are continuous. And for what we're going to talk about now with hitting locations, the big change here is when I hit this object K, I'll generally hit it on the inside because this process is making jumps. So you're not going to be concentrated just on the barrier again. The Hausdorff dimension of the image is generally, so if your dimension's about 2 or above, you're going to have Hausdorff dimension alpha. You have a fractional dimension for the image of this path. Okay, so I'm actually talking quite quick, so I guess I will get through all this. So I want to talk a little bit about this idea of walking in and out of balls. What we're going to do here is use this paper by Blumenthal, Couture, and Ray in 1961 that gave some expressions for hitting the balls with an alpha stable motion. You can always use scaling so that if we want to hit a general ball, we can always shift it so it's centered at the origin and scale it. And if we solve that problem, then we can solve the original problem. Okay, so what Luc Devroy and I have worked on is to find computationally useful ways of implementing the formulas in this paper. So we'd like to know the probability of hitting a ball if we start from some point outside the ball. And we're focusing on balls here because, frankly, balls are the only thing that we can really handle exactly. Okay? And what's behind this is if we know how to work with balls, we can start using that to build up hitting more complicated sets. So we can calculate the probability of hitting a ball. We can simulate hitting location of the ball, starting from an outside point. We can calculate hitting locations for leaving a ball if we start inside the ball. And we can simulate from the equilibrium distribution of the ball. And as I said, the real goal here, which I won't really have time for, is to show that to use these concepts for balls and how to approximate and study a more complicated object. So have I been talking so fast? Because I thought I'd probably be running out of time here. Anybody still awake? Okay, so next several pages will give you some of the results we have and show you some of the simulations. Okay, so in this paper I mentioned by Blumenthal et al., there's an integral expression for the probability. And while correct, it's not very easy to use that integral expression because we're going to want to run these programs. So I didn't say this clearly before. To get a good idea of a capacity, we may have to generate 1 million random walks. Okay, so whatever we're going to be doing a lot of times. Right? And in fact, Jack Douglas had done something with taking a database of proteins that I think had some hundreds or thousands of complicated proteins and running the Zeno program on each of them. So generating, say, 1 million paths for each of these thousands of objects. Okay, so we need to be able to do things fast. Okay, so it turns out that with the change with transformation, you can relate that integral to a beta distribution. So statisticians will understand what a beta distribution is. The analysts, it's related to the incomplete beta function. Okay, so if capital F is the cumulative distribution function of a beta distribution with these two shape parameters, then we can find the probability of hitting a ball, given that you start at a location X, is 1 over the absolute value of X squared. Okay, so the point is that this quantity is a well-known quantity and there's efficient and accurate algorithms for calculating this quickly. Here's a little plot of the probability of hitting the ball, given that we start R units away. This is in dimension 3 as we vary this index alpha between 0. Sorry. I don't know which way does this go. Can't quite see, it's too small. One of these is the alpha equals to the Brownian case, the Gaussian case, and as we change alpha, we get different curves here. Oh, I want to say another thing that we've tried to do in this work is make it general so that we can change the dimension. Most practical interest is in dimensions 2 and 3, but it'd be nice to be able to do this in higher dimensions. And there's some reasons to do at least some of that. And so we want to be able to do this for any alpha between 0 and 2, and we want to be able to do it in any dimension. Okay, one of the key steps in doing this is this key idea. So if I have a ball and I start from outside this ball, I want to simulate from the possible hitting locations, and I want it to be able to do it with the right probability. If I end up here, I'm ending up here with the right probability. Not just that I'm all locations, it's just I'm covering the ball. Some points, some regions are more likely than other regions. So we want to do that correctly. So here's some R pseudocode for doing that. So here, lambda be the length of the vector x. So this is how far away you are from the origin. Okay. Again, we've normalized things, so we're looking at the unit ball that's centered at the origin. So we have to be starting outside the ball, so lambda has to be bigger than 1. Okay. So here, it's a simple rejection algorithm. We're going to repeat this loop until this condition holds. So this is the R function to return a random beta distribution that has these two shape parameters. Then I need to generate, the next 2 lines generate a random direction on the sphere in dimension d-1. And so there's a common way of doing this. You generate d univariate independent normal random variables, and then you take that vector and divide it by its length. That'll automatically give you a point on the surface of the unit sphere, and because of the independence of the random variables, it turns out to be uniform on the sphere. This works in any dimension. Okay, so now I have Q and Z. Q that's beta, has a beta distribution, and Z that has uniform on the sphere in the appropriate dimensions. And we define Y to be the square root of Q times Z. So remember, Z is a vector now. Q is a scalar. So we scale that location. Okay. And then we generate a uniform 0, 1 random variable. And then we test, is that U less than this quantity, lambda minus 1 squared over the norm of x minus y to the dth power. Okay. So you repeat this loop until this condition holds. Okay, this is an illustration of what's called rejection. A rejection method for generating a certain distribution. It's used when there's no explicit way to do that. Basically, we're generating something close. This beta, square root of the beta times a uniform distribution. And then a certain fraction of those we throw away and a certain fraction we keep based on this condition. Okay, so here's some simulations here. I think there are 5,000 simulations here. When alpha equals 2, it's the Brownian case. So in all these cases, I'm starting over here. It's not shown on the map, but I think I'm like 2 units, no, 1.5 units away from the origin, out here on the x-axis. Okay. So the Brownian case, all the hitting points are on the surface of the sphere, and it's a little hard to see, but there are more of them over here and less of them as you move around than fewest over here. As we lower this parameter alpha, remember we're now talking about a process with jumps, so we're going to hit on the inside. And we get a distribution of points like this. Okay. Again, we're starting over here to the right, so it's more likely we hit on this region. And it gets less and less likely as we move into the inside. As we lower alpha even more, there's more and more jumps that are bigger. Sorry, they're bigger and bigger jumps. So it's, even though it's still concentrated here, things are getting more spread uniformly over the whole disk. And then here, when alpha is 0.5, it's even more spread out. And here's a picture with a fixed lambda. So I'm going to start from a point on the x-axis. So the first one is lambda is equal to 2. So here's the origin, here's 1. So somewhere around here is where I'm starting. If I do that and run this process, I think with alpha is 1.5 here, we get points like this. As I move the point in, so now I'm starting closer in here at 1.25, we see it's getting more concentrated here. Lambda gets even smaller, 1.1. See, it's getting more tightly concentrated here. Lambda is 1.01. It's more and more concentrated near here, and you're getting very few points over here. So as this random walk goes around, this corresponds to our intuition. It's more likely that we're going to, if we start really close, it's more likely that we're going to hit really close to that point. And here's a picture in 3 dimensions. The starting location is off here to the right a little bit. And you can see how it's hitting in the sphere. Again, more concentrated, close to where we started. Okay, so we got this to work last year. And then as we started to use it, we said, well, there's a problem here. If you do an analysis of this, it turns out that the number of iterations, remember we had this loop in the rejection method, the number of iterations is of this order. So remember, it's the distance of the starting point from the origin. And in particular, so you take lambda plus 1 over lambda minus 1 to the power, to the dimension. And of course, that blows up as we get closer and closer to the surface of the ball. And this is a problem because if we want to do this millions of times, and as we have a complicated object, we're going to want to get closer and closer to it. And therefore, as we get closer and closer, it's going to take longer and longer to get there. And you're going to have, but it'll eventually, it should happen, but eventually maybe a period of hours or days instead of seconds. Okay, so we have this simple rejection method that works, but it's very slow when you start close to the object. Okay, so we came up with 2 other methods. The first one is basically a way to use symmetry to reduce to a 2-dimensional problem. And then once we've got a 2-dimensional problem, we do a rotation around the x1 axis to get our final result. I don't want to do all the details here because we'll be here for too long. So this is essentially gives us a transformed simple rejection method. And it works, gives the same kind of answers, but it has the same problem with execution time. But we can improve it. So we have spent several months on this, and it's a headache. The basic idea is we're going to be simulating a point in the unit ball. What we do here, here's a picture in 2 dimensions, is we partition the unit ball into different regions. So I didn't have an easy way of drawing this, so I just simulated points in the region. That's why this figure's a little bit fuzzy. So this black region over here are regions there where we're less likely to hit and we can efficiently estimate things. This region in here, this colored region, is where we're more likely to hit as we get closer, our starting point gets closer and closer to the ball, the unit ball. So the red is in this region, but it's kind of farther away. And we have this blue region here, we have a green region up in here. And so basically what we do is we partition this into different regions. We deal with it over a transform space where here's the image of those different partition elements. And then on each of these pieces, we use a different method, clued to how big lambda is. The bad news is that it's a pain. It's rather painful using beta functions, and there are constants that come up in the calculations like 4 over the square root of 31 and ugly expressions that come up. The good news is when we put all the pieces together, we get something that's uniformly bounded in the expected number of iterations. Okay, so there's still a rejection, a loop going on when we reject. But by making the upper bound for the rejection tailored to the region, you can make it much more efficient. In fact, if you do it this way, you actually have an uniform upper bound on the expected number of iterations. So this is uniform in where we start, no matter how close to the ball we get, it works. No matter what alpha is, no matter what the dimension is. So, and I think actually the expected number of iterations is less than or equal to 15 for all cases, all dimensions and all alpha, and all starting locations. Okay, so about the last thing I'm going to do is do the opposite problem. I didn't do a picture for this, but there are cases where we want to look at sort of the complementary problem. So I want to start inside the unit ball and run this process until I leave. So if it was Brownian motion, I would, since I have continuous paths, I would always hit the boundary somewhere. If it's stable motion, in general, I will jump over that boundary. So I could be anywhere, in theory, anywhere as far away as you want to look at. Okay. So to simulate that, we have to treat two cases separately. So the easiest case is when I'm starting from the origin. So again, we've reduced things to the unit ball. I start at the origin. The density of the hitting locations is given by an expression like this. So again, these are messy problems. You have these funny, ugly constants coming up. You've got a gamma function here. You've got a sine of pi alpha over 2 here. A fractional power of pi here. But this is the density of the hitting locations. This is radially symmetric. So you can simulate this by taking R, where R is just the magnitude of X, amplitude or magnitude, and Z is the uniform on the sphere in the dimension that you're looking at. So you can do this for any radially symmetric distribution. The problem is, can you determine what's the distribution of this radial component? So using radial symmetry, you can go through some calculations and find that the density of the radial distribution is given by this expression. And then a change of variable shows that you can get this density by taking 1 over the square root of a beta random variable where it has these two parameters, shape parameter alpha over 2 and 1 minus alpha over 2. Okay. And the surprising thing, at least to me in all this calculation, is there's no dependence on the dimension. This formula for picking R doesn't not care whether you're in 2 dimensions or 3 dimensions or 97 dimensions. All you have to do is generate something that's uniform on the sphere to be able to simulate this. The other case is where we're not starting at the center of the ball. And here there's a clever idea. We tried to do this directly, but it gets very complicated. Then we realize we can use Ries's idea of duality. So remember, we're starting at a point inside the ball. And what duality lets us do is to reflect that point through the sphere. So we get a point that's outside of the ball. Then we can use the algorithm we have above for running this until we hit the ball. And then we can take that location, say y prime, and reflect it across through the sphere again. And that gives us a point outside. It turns out that's exactly the answer you need. So duality comes and saves the day again. So here's some pictures. On the left side, we started here at this star. And here there are 5,000 simulations. Can you see that? I'm not sure how clear that is on screen. You see here alpha is 1.5, starting from the origin. And we get this cloud of points getting less and less likely as we spread out. They're more concentrated around the ball. If I lowered alpha, where I have bigger jumps, we'd see points spreading out and being more farther away. And then here's a case where we're exiting from the ball when we start over here where this star is. So we're starting not at the center, but a different point. So we use duality to reflect that. So we point out here, run a random walk, and then reflect it again to get this cloud of data points. And that is it. So here's some references for this work. And I will stop here.
Thank you very much, John.
Mhm.
Any questions?
I have a couple of questions, but I also would like to start with a remark. First of all, John, that was a spectacular talk. Very, very much enjoyed it. Jack, it's a pleasure to see you. And I would like to make sure that people know that on the 24th of October, we're having a conference for harmonic analysis in our region, and Jack will send you notices about this.
Oh.
But in the 3 to 4 time slot, I've arranged for what I'll call the AU All-Stars to give talks, and one of these All-Stars is Professor Nolan, but we'll have Professor Bukovalis, Professor Nolan, Professor Art Shapiro from the CS and Psych Department, and Professor Barone will all be giving presentations relative to their work in harmonic analysis. So the second is, John, when you say characteristic function, I immediately think Fourier transform. So x of negative absolute value t, that's a Cauchy, right? X of negative, well, t squared, that's Gaussian. And the x of t, absolute value t alpha, only two of those are the Levy, and only two of those, if I'm correct, are known in the in closed form.
So the joint characteristic is a multivariate Fourier transform up to a constant. So that was, I think you're talking about here. So if alpha is 2, you have Brownian motion. If alpha is 1, you have a Cauchy process.
Yeah.
And for all other values of alpha in this region, you have an alpha stable process. Those first two are the ones where you have explicit formulas for the multivariate densities. In the other cases, there are no explicit formulas. There are some numerical techniques. In fact, going back, I think over 20 years now, one of my PhD students, Abdul Hamid Hussein, wrote the first programs to calculate some for a couple of different values of alpha.
Excellent. And then one last question. And if these are done with random walk in Euclidean geometry, but if we change the underlying geometries to say something, I don't know, something like people like me are interested in hyperbolic. I remember results of Thurston about random walks in hyperbolic space, how they are recurrent, and with probability 1, a random walk in hyperbolic space, in two-dimensional hyperbolic space, will hit any fixed object in the space. Are there analogs of all these results for different geometries?
I don't know. I know of work on random walks on manifolds. I don't know about different geometries.
No, it all formally extends to any dimension of space. And although the 2 dimensions deserve special mention, because there you have the logarithmic capacity, and because the walks become recurrent, you have to play the game somewhat differently. But McKean has shown how formally you can do the same kind of random walk kind of algorithm, and sort of generally speaking, but accounting for the recurrent character. That's never been implemented numerically, so that would be fun. And of course, then you have all kinds of conformal invariants, and
Yeah.
Yeah,
because by uniformization, there's 3 fundamental.
Transfinite diameter, and all these things are kind of come into play.
Excellent, thank you.
So that's very rich territory. And also, I should say that we're using this for all kinds of. First of all, the biologists deserve special mention here, because the original algorithm, it isn't Juba. It goes back to biologists. They're very keen on capacity because it relates to rate constants for diffusion limited reactions and ligands and receptor binding on the surface of cells. So they were very intensely studying that for many years. And they made really important contributions to the early stages of the development of the algorithm that go way back. I don't even know where. It's sort of a difficult matter even to find out who did what when and how this all came about in terms of development. But it plays a big role in field theory, critical phenomena, Semantic, capacity is right at the core of you know, field theories of phase transitions and high energy physics. You know, in statistical mechanics, the capacity plays the critical temperature of the spherical model, and diverse other systems can be exactly formulated in terms of these same objects. So anyway, they're very central in physics. And then as a final point, there are all kinds of PDEs. This is just one PDE he was talking about. So one that we've spent a lot of time thinking about is the polarizability, magnetic and electric. These come up in properties of materials. When you have split stuff and other stuff, the properties of the stuff changes, and the measure in your effective medium theory of how the properties change involve these same, you know, solving Laplace's equations with complicated shaped objects in general and generalized boundary conditions.
That's a fair of a problem. Solving Laplace in like a general Lie group is a lot of fun.
Yeah. So anyway, there are classically difficult problems. As the cube example that when Polya tells you you can't do it, you can probably believe him.
Yeah.
And so yeah. So anyway, there are not anyone who wants to get involved. That was just a general invitation because you know, we did make a lot of progress with the polarizability, but say the Neumann problems are particularly nasty, or at least people haven't figured out usually there's an angle you have to develop. And so, you know, there hasn't been a kind of an effective strategy for certain kinds of boundary value problems. So it's a really, I think, kind of an interesting and challenging area. And I'm really glad that John has become involved, because I think hopefully he'll get other mathematicians interested in this. It's really a great topic. I think that's, in addition to even getting specific results, I think there's potential. And I think, you know, in this whole idea, I mean, there are all kinds of young people that have laptops. And my great hope is that you can actually do all kinds of shape characterization problems in this way and characterize, and we didn't get into that, but you know, there are isoperimetric inequalities associated with all these shape functionals that allow you to put, you know, indices, pure numbers to any shape sets to classify them. And for many purposes, we have polymers, and so we study them, but there's nothing, you know, the ideas are way more general. And I think it would be really cool to see some of these ideas of probabilistic potential theory to kind of merge, you know, go into say even the undergraduate curriculum, if, you know, I'm dreaming there, but maybe the undergraduates. And I think they could start solving all kinds of problems in this. And it's also it's very intuitive. Once you get, like he didn't talk about it, flow through arbitrary shaped pipes, the torsional rigidity of arbitrary shaped, you know, beams, all kinds of very complicated boundary value problems can be formulated exactly this way. And sometimes the accuracy is spectacular. I mean, before you'd struggle with finding an element to get a couple significant digits, you know, in your field in space, you can get 6 more than, you know, many significant digit accuracy by the instead of conversion.
You're talking, Jack, you're talking about Brownian motion, right? Is it
No, obviously.
Is the same thing true for stable processes? You can get.
Well, we'll see. In principle, I would say, you know, there's certain efficiency things, as we've, you know, even in the case of the Brownian motion, it started out and still is highly inefficient for certain boundary value problems, even though in principle, you've kind of solved the problem. You could be like Kakatani in 1943, and you write down the equation and you've solved it, you're done. But then there matters of practicality of actually getting an accurate solution based on that formal statement in terms of paths. And that is much of an art at this stage. And you know, and so it goes through various stages of refinement. And for example, this work by Juba, there were a lot of things that went into the optimization of that program to make it work. It was over 1,000 times faster than the original version that I was sort of involved with Mark Mansfield, and that was built on work by other people. That, you know, so there's a whole hierarchy of improvements that come in time. But I do think in time, I don't see any reason why it can't be as efficient in principle, and the accuracy, you know, potential is extremely high for solving all kinds of PDEs. You know, it's.
Is there a PDE associated with the hitting time for a stable process?
Yes, you can solve the fractional Laplacian problem.
So,
Yeah.
and that is associated with the unit ball or a ball. So why don't you do that? I mean, if you have very complex regions, I understand why you would want to do a simulation, but if it's just the unit ball, why can't you solve the differential equation?
So I think you can on the unit ball, but the issue
But
is,
all over
I'm
after
talking,
the unit
your
ball.
simulations are right now just for the ball, right?
no, well, what I showed you was for the ball. Can I get back here? That what I didn't have time to talk about is these steps where we build on what we can do for the unit ball lets us generalize to walk on spheres for general shapes.
Yeah, that's the whole point. So we have actually many different sort of ways of specifying the shape, collections of balls. You know, there could be discretized objects in terms of, you know, pixels. Anyway, our Zeno, the program, gives you a kind of whole palette of ways of representing the object, you know, surface plaquettes, whatever. But the idea is the general, any shape that you throw at me, and like for the polymers, any kind of garden variety polymer, you may need, you know, you generate by molecular dynamics, say 10,000 or at least 1,000 configurations for any given type of polymer of any different length. So, and then you need to calculate for every member of the ensemble. You see, it can take a lot of, you have to be highly efficient in your computation to really get accurate numbers for such stochastically defined objects. So, and so that's been achieved with the Zeno, and not just for capacity, but for these other properties too that are related to how, you know, you probably know about Einstein's result for the intrinsic viscosity, you know, how the putting spheres in a solvent changes the viscosity of a solvent. So now we want to do something, and so we have maybe ellipsoids and a couple other objects, and you know, mathematicians and physicists work very hard at that. But now we can do anything, any object that you or
Well,
you know, you say
we're
you put
talking
an
about
arbitrary
Brownian
shaped
motion,
object
right?
of some
No.
conductivity into. Yeah, well, all those problems are now. Getting back to more general cases, you look
Actually,
at alpha
can I hold that
processes,
for
which I
just
guess
a
is the
second?
topic of the day.
Maybe we should,
Yeah.
Well,
Yeah.
well, John, so
Okay.
right now you can do any compact set?
yes. So maybe 1 second. Maybe we should release people,
Let people
those that want to leave. Thank you for attending.
Yeah.
But if Jack and Charles and anyone else have any questions, you can stick around. Okay, thank you,
Okay.
everyone.
Thank you very much,
And I
John.
think we should thank the speaker for a wonderful talk.
Yay.
Absolutely.